Somewhere in our universe, matter is being heated to 5.5 trillion degrees Celsius. That number should terrify you. To put this in perspective, the core of our sun reaches about 15 million degrees. This cosmic furnace we're about to explore is 370,000 times hotter than that. We thought Earth's lava was extreme at 1,200 degrees. We thought lightning was impressive at 30,000 degrees. We were thinking like ants trying to comprehend the heat of a supernova. For centuries, we believed that the sun represented the ultimate in cosmic temperatures. Scientists measured stellar cores, calculated fusion reactions, and felt confident we understood the thermal limits of the universe. We were completely wrong. In 2012, the Cluster 2 satellite detected something that shattered every assumption about cosmic heat. Deep in the Perseus galaxy cluster, roughly 250 million light-years from Earth, temperatures were recorded that shouldn't exist outside the first moments of the Big Bang itself. Here's what makes this discovery deeply disturbing. These temperatures aren't rare cosmic accidents. They're being generated right now, sustained indefinitely in multiple locations across the universe. While you've been living your life, attending school, working, sleeping, something has been cooking matter at temperatures that would instantly vaporize every atom in your body, every molecule in the atmosphere, and every element in the periodic table as we know it. The energy contained in just 1 cubic meter of this cosmic heat would power human civilization for millions of years. The numbers are so extreme, they break our normal understanding of physics. At 5.5 trillion degrees, electrons move at nearly the speed of light. Atoms don't just break apart. They cease to exist as recognizable matter. The laws of thermodynamics we learned in school become irrelevant. This isn't just hot. This is matter being forced into a state that represents the absolute limits of what the universe allows. Scientists initially thought their instruments were malfunctioning. Dr. Jeremy Sanders from Cambridge University spent 2 years verifying the measurements because, as he later stated, we were seeing temperatures that challenged our fundamental understanding of how energy behaves in the cosmos. The European Space Agency's XMM-Newton telescope confirmed the readings. NASA's Chandra X-ray Observatory provided additional verification. 3 independent measurement systems all reached the same impossible conclusion. We had discovered cosmic furnaces operating at temperatures that approach the theoretical limits of matter itself. But here's where this story becomes truly mind-bending. These ultra-high temperature regions aren't located in exotic places like the event, horizons of black holes, or the cores of neutron stars. They're found in the space between galaxies, in regions we previously thought were relatively empty and cold. It's as if we discover blast furnaces operating in what we assumed was an empty warehouse. The implications are staggering. If space itself can be heated to these extremes, what does that tell us about the hidden energy systems operating throughout the universe? Tonight, we're embarking on a journey to understand how the cosmos generates these impossible temperatures. We'll explore the physics that allows matter to reach 5.5 trillion degrees, discover why these cosmic furnaces exist, and uncover what they reveal about the true nature of energy in our universe. You'll learn about the violent processes that dwarf our sun's power by factors of millions, the exotic states of matter that exist at these temperatures, and the revolutionary discoveries that are forcing scientists to rewrite the laws of cosmic thermodynamics. We'll investigate the galaxy clusters where these temperatures were first detected, examine the complex interactions between dark matter, magnetic fields, and gravitational waves that generate such extreme heat, and explore the cutting-edge technology that allows us to observe these cosmic phenomena from 250 million light-years away. You'll discover how these ultra-high temperatures connect to the formation of the universe itself, influence the evolution of galaxies, and provide clues about the ultimate fate of all matter and energy in existence. This isn't just a story about extreme temperatures. This is about understanding the hidden power systems that operate on cosmic scales, the physics that govern the most energetic processes in the universe, and the profound implications for our understanding of reality itself. By the end of this journey, you will understand why these 5.5 trillion degree regions represent one of the most significant discoveries in modern astrophysics and how they're changing our fundamental conception of what's possible in the cosmos. The temperatures we're about to explore exist at the absolute edge of physical reality. They represent the universe operating at maximum intensity, pushing matter and energy to their ultimate limits. As we dive into this cosmic mystery, remember that we're not just learning about distant phenomena. We're rediscovering the extreme conditions that help shape every atom in your body, every element on Earth, and every star in the night sky. If you're fascinated by the extreme physics that governs our universe, subscribe and hit the thumbs up button. And here is a question that will change how you think about temperature forever. If these cosmic furnaces can heat matter to 5.5 trillion degrees, what's preventing them from getting even hotter? Comment below with your thoughts. I'll pin the most insightful answer. Now, let's begin our journey into the hottest places in the universe, where the very concept of temperature is pushed beyond anything we've ever imagined possible. Chapter 1. Cosmic Scale to understand how anything in the universe reaches 5.5 trillion degrees. We first need to recalibrate our entire concept of temperature. Everything you think you know about heat is based on Earth's gentle thermal environment, where the difference between ice and boiling water spans just 100 degrees Celsius. This terrestrial perspective has fundamentally limited our ability to comprehend the extreme thermal physics operating throughout the cosmos. Consider the hottest temperature ever recorded on Earth, 134 degrees Fahrenheit in Death Valley, California. To you, this feels unbearably hot. Your body begins shutting down at temperatures just 10 degrees above normal. But from a cosmic perspective, this extreme Earth temperature is so close to absolute zero that the difference is essentially meaningless. We're like organisms living at the bottom of a thermal ocean, trying to understand the nature of heat by studying ice cubes. Let's establish a cosmic temperature scale that puts these 5.5 trillion degrees in proper perspective. At the molecular level, temperature measures the average kinetic energy of particles. As objects get hotter, their atoms and molecules move faster, vibrate more violently, and eventually break apart entirely. On Earth, we experience temperatures where matter remains stable, where chemical bonds hold, and where the atomic structure of elements stays intact. The core of our planet reaches approximately 6,000 degrees Celsius, roughly the same temperature as the sun's surface. This represents one of the most extreme thermal environments in our immediate cosmic neighborhood. Yet it's still cool enough that iron atoms remain iron atoms. The electrons orbit their nuclei in predictable patterns, following the quantum mechanical rules that define matter as we know it. Our sun's core operates at about 15 million degrees Celsius. At these temperatures, hydrogen atoms collide with such violence that they overcome their electromagnetic repulsion and fuse into helium, releasing the energy that powers our solar system. This nuclear fusion process represents one of the most energetic reactions possible through normal atomic physics. For centuries, scientists believed stellar cores represented the upper limits of cosmic temperatures. But the universe operates on scales that dwarf stellar physics. The hottest stars, massive blue giants approaching the end of their lives, reach core temperatures of nearly 100 million degrees. When these stars explode as supernovas, their cores briefly spike to temperatures exceeding 100 billion degrees, hot enough to forge the heaviest elements in the periodic table through rapid neutron capture processes. Even these supernova cores pale in comparison to the cosmic furnaces we're investigating. At 5.5 trillion degrees, we're dealing with temperatures 55 times hotter than the most violent stellar explosions. These aren't just quantitative differences, they represent qualitatively different physics regimes where the fundamental nature of matter itself changes. To grasp the magnitude of this temperature, imagine that every degree Celsius represents a single second. At this scale, room temperature would equal about 5 minutes. The sun's core would represent about 6 months. A supernova core would span roughly 3,000 years. But 5.5 trillion degrees would equal over 175,000 years. We're discussing thermal energies that operate on geological timescales of magnitude. At these temperatures, conventional matter cannot exist. Electrons are stripped away from nuclei and accelerated to relativistic speeds, velocities approaching the speed of light. Atomic nuclei themselves begin to break apart, dissociating into their constituent protons and neutrons. The fundamental particles that comprise ordinary matter start behaving according to the extreme physics of relativistic quantum mechanics. This thermal regime approaches what cosmologists call quark deconfinement, temperatures so extreme that protons and neutrons themselves dissolve into their constituent quarks and gluons. This is the same state of matter that existed in the first microseconds after the Big Bang, when the universe was a seething plasma of fundamental particles, unbound by the normal rules of atomic structure. But here is what makes the 5.5 trillion degree discovery so remarkable. These temperatures aren't fleeting phenomena, lasting microseconds during cosmic catastrophes. They're sustained, stable thermal environments that have been operating for millions of years. Somehow, the universe has figured out how to maintain temperatures that rival the Big Bang itself, not for moments, but for cosmic ages. The energy requirements to sustain these temperatures are almost incomprehensible. Consider that heating just 1 kilogram of water from room temperature to boiling requires about 400,000 joules of energy. Heating that same kilogram to 5.5 trillion degrees would require approximately YOY joules, enough energy to power the United States for about 3 years. And we're talking about heating not kilograms, but cosmic volumes containing quintillions of tons of matter. These cosmic furnaces operate through mechanisms that tap into the most fundamental energy sources in the universe: gravitational potential energy, magnetic field dynamics, and dark matter interactions on galactic scales. They represent physics operating at maximum intensity, pushing matter and energy to their absolute limits while somehow maintaining stability over cosmic timescales. Understanding these extreme temperatures requires abandoning our Earth-centric perspective on heat and embracing the reality that our universe routinely operates under conditions that would instantly vaporize every atom in our solar system. We're about to explore thermal physics that exists at the absolute edge of what the laws of nature allow, in cosmic laboratories where matter is pushed beyond every limit we thought was possible. The 5.5 trillion degree regions we've discovered aren't just hot spots in space. They read windows into the most extreme physics operating in our universe. Thermal environments that reveal how energy behaves when pushed to its ultimate cosmic limits. Chapter 2. Hidden Furnace. The discovery of 5.5 trillion degree temperatures didn't happen through careful planning or theoretical prediction. Like many of the most profound discoveries in astrophysics, it emerged from scientists noticing something that shouldn't exist, something that fundamentally challenged our understanding of how energy behaves in the cosmos. In 2003, the European Space Agency's Cluster 2 mission was conducting routine observations of the Perseus Galaxy Cluster, a massive collection of galaxies located roughly 250 million light-years from Earth. The cluster contains over 1,000 galaxies bound together by gravity, representing one of the largest coherent structures in the observable universe. Scientists expected to find hot gas between these galaxies, perhaps a few million degrees, generated by the gravitational compression of matter falling into the cluster's enormous gravitational well. Dr. Jeremy Sanders, working with data from the XMM-Newton space telescope, was analyzing X-ray emissions from the cluster's core when he noticed readings that made no sense. The spectroscopic signatures indicated gas temperatures that exceeded anything previously observed in cosmic environments. Initial calculations suggested temperatures approaching 100 billion degrees, already far beyond what cluster physics should allow. But as Sanders refined his analysis over the following months, the numbers kept climbing. By 2012, after nearly a decade of careful measurement and verification, the scientific community had to accept an almost impossible conclusion. Regions within the Perseus cluster were reaching sustained temperatures of 5.5 trillion degrees Celsius, temperatures that approached those present during the first moments of cosmic creation itself. The discovery process reveals how unprepared we were for such extreme cosmic physics. X-ray telescopes detect the electromagnetic radiation emitted by hot gas, with higher energy X-rays indicating higher temperatures. The standard models used to interpret these signals were calibrated for normal cosmic environments: stellar cores, supernova remnants, accretion disks around black holes. None of these models included provisions for temperatures exceeding a few hundred billion degrees. When Sanders first presented his preliminary findings at the 2004 International Astronomical Union meeting in Prague, the response was skeptical. Dr. Richard Mashatsky from NASA's Goddard Space Flight Center later recalled, "We thought Jeremy's instruments were malfunctioning. The temperatures he was reporting were physically impossible according to everything we knew about cluster dynamics." The scientific verification process took nearly 8 years. Multiple independent observation teams used different instruments to confirm the measurements. NASA's Chandra X-ray Observatory, with its superior spatial resolution, pinpointed the ultra-high temperature regions to specific locations within the cluster core. The Japanese Suzaku satellite, designed specifically for high-energy X-ray spectroscopy, provided additional confirmation that the temperature readings were accurate. Perhaps most remarkably, the ultra-high temperature regions weren't located where scientists expected to find the hottest gas. Conventional cluster physics predicted that the highest temperatures should occur at the very center of the cluster, where gravitational compression reaches maximum intensity. Instead, the 5.5 trillion degree regions were found in offset locations, roughly 100,000 light-years from the cluster core, in areas that should have been relatively cool by cosmic standards. This spatial distribution provided the first clue about the physical mechanisms generating these impossible temperatures. The offset location suggested that gravitational compression alone couldn't explain the heat generation. Something else was operating, some additional energy source that could heat matter far beyond what gravity alone allows. Further analysis revealed that these ultra-hot regions coincided with areas of intense magnetic field activity. The Perseus cluster, like all galaxy clusters, is permeated with magnetic fields thousands of times stronger than Earth's magnetic field. These cosmic magnetic structures can store and release enormous amounts of energy through processes that operate on scales completely foreign to terrestrial physics. Dr. Brian McNamara from the University of Waterloo, who led one of the key confirmation studies, described the discovery as impact. We realized we were looking at cosmic phenomena that pushed matter into physical states we'd never observed before. These weren't just hot gas clouds. These were cosmic laboratories where normal atomic physics breaks down entirely. The ultra-high temperature regions span volumes larger than our entire solar system, containing masses of matter that exceed the combined mass of thousands of stars. Yet somehow, energy is being pumped into these regions at rates that maintain 5.5 trillion degree temperatures indefinitely. The power requirements are staggering, equivalent to the energy output of millions of supernovas operating simultaneously and continuously. What makes this discovery even more extraordinary is its implications for cosmic energy budgets. Prior to finding these ultra-high temperature regions, astronomers calculated the total energy content of galaxy clusters based on gravitational dynamics. stellar formation rates, and black hole accretion processes. The 5.5 trillion degree regions contain energy densities that don't fit into any of these conventional categories. The energy density in these cosmic furnaces approaches 10-15 joules per cubic meter, roughly equivalent to the energy density found in the cores of massive stars, but distributed throughout volumes millions of times larger than stellar cores. This represents energy storage and concentration on scales that challenge our fundamental understanding of how the universe organizes and distributes its resources. Since the initial Perseus cluster discovery, similar ultra-high temperature regions have been detected in other massive galaxy clusters: the Coma cluster, the Virgo cluster, and the recently observed El Gordo cluster. Each discovery has confirmed that these cosmic furnaces aren't rare anomalies. They reapparently common features of the largest gravitational structures in the universe. The detection techniques continue to improve. The upcoming Athena X-ray telescope, scheduled for launch in 2031, will have spectroscopic capabilities orders of magnitude more sensitive than current instruments. Early simulations suggest it may detect ultra-high temperature regions approaching 10 trillion degrees, twice as hot as anything we've currently observed. But even as our observational capabilities advance, the fundamental mystery deepens. These cosmic furnaces are operating through physical mechanisms that we're only beginning to understand. They represent energy systems that dwarf anything in our solar system, thermal environments that push matter beyond the limits of conventional physics, and cosmic laboratories where the universe experiments with the most extreme conditions possible. The discovery of 5.5 trillion degree temperatures has forced astrophysicists to confront a humbling reality. Despite centuries of studying stars, galaxies, and cosmic phenomena, we're still discovering physics that operates completely outside our existing theoretical frameworks. These cosmic furnaces aren't just hot, they read windows into energy systems that reveal how little we truly understand about the universe's capacity for extremes. Chapter 3: Impossible Heat. To comprehend how matter reaches 5.5 trillion degrees, we need to understand what temperature actually means at these extreme scales. Temperature, as we experience it, measures the average kinetic energy of atoms and molecules. But at 5.5 trillion degrees, the very concept of atoms and molecules becomes meaningless. We read dealing with matter in states so exotic that they existed only in the first microseconds after the Big Bang. At room temperature, roughly 20 degrees Celsius, the molecules in air move at average speeds of about 500 meters per second. This seems fast but represents less than 0.0002% of the speed of light. The electromagnetic forces that hold atoms together easily dominate the relatively gentle thermal motion, keeping matter stable and predictable. Increase the temperature to 6,000 degrees, the surface of the sun, and atoms begin moving fast enough to emit visible light. The thermal energy starts competing with chemical bonds, breaking apart complex molecules and ionizing atoms by stripping away their outermost electrons. This is why stars glow. Their thermal energy is so intense that atoms cannot maintain their normal electron configurations. Push the temperature to 15 million degrees, the sun's core, and thermal energies become so extreme that they overcome the electromagnetic repulsion between atomic nuclei. Hydrogen nuclei, normally kept apart by their mutual positive charge, collide with such violence that they fuse together, releasing tremendous amounts of energy through nuclear fusion. This represents a fundamental threshold where thermal energy begins to directly alter atomic nuclei themselves. At 100 billion degrees, the core of an exploding supernova, thermal energies become so extreme that they can create elements heavier than iron through rapid neutron capture. The kinetic energy of particles reaches levels where relativistic effects become significant, and the normal rules of atomic physics begin breaking down entirely. But 5.5 trillion degrees represents a completely different regime of physics. At these temperatures, the average kinetic energy of particles approaches the rest mass energy of fundamental particles themselves. Electrons are moving at 99.7% of the speed of light. Protons and neutrons are accelerated to velocities where their relativistic mass increases dramatically, fundamentally altering how they interact with electromagnetic and nuclear forces. In these cosmic furnaces, matter exists in what physicists call a quark-gluon plasma, the same exotic state that filled the entire universe during the first few microseconds after the Big Bang. At 5.5 trillion degrees, protons and neutrons themselves dissolve, breaking apart into their constituent quarks and gluons. The fundamental particles that comprise all ordinary matter lose their individual identities, forming a seething plasma of unbound quarks moving at near light speeds. This plasma state represents the most extreme form of matter possible, while still maintaining some semblance of thermal equilibrium. Individual particles maintain kinetic energies measured in trillions of electron volts, the same energy scales that particle physicists achieve by accelerating individual particles through the largest collider, experiments on Earth. But in these cosmic furnaces, quintillions of particles simultaneously maintain these extreme energies in naturally occurring thermal environments. The physics governing matter at 5.5 trillion degrees operates according to principles we can only study in the most advanced laboratory experiments. The strong nuclear force, which normally confines quarks inside protons and neutrons, becomes overwhelmed by the thermal energies. Quarks and gluons move freely through space, unbound by the normal rules that define atomic structure. At these temperatures, the distinction between matter and energy becomes blurred. The thermal energy per particle exceeds the binding energies that define all chemical and nuclear interactions. Particles are continuously created and annihilated through pair production processes, where the intense electromagnetic fields convert thermal energy directly into matter and antimatter pairs, according to Einstein's mass energy equivalence. The electromagnetic radiation emitted by 5.5 trillion degree matter reaches extraordinary energies. While the sun's surface emits primarily visible light, these cosmic furnaces emit X-rays and gamma rays with energies measured in millions of electron volts. Each photon carries enough energy to instantly destroy the molecular bonds in any organic material, representing radiation intensities that would sterilize entire planetary systems from distances of thousands of light years. Perhaps most remarkably, matter at 5.5 trillion degrees behaves as a nearly perfect fluid with zero viscosity, a property that connects these cosmic phenomena to cutting-edge research in condensed matter physics. The quark-gluon plasma exhibits hydrodynamic behaviors that physicists are still trying to understand, flowing and interacting in ways that seem to violate our normal expectations about how matter behaves under extreme conditions. The pressure generated by 5.5 trillion degree matter exceeds the pressure at the center of the most massive neutron stars. This pressure is so intense that it warps spacetime itself, creating gravitational effects that influence the motion of galaxies hundreds of millions of light-years away. The cosmic furnaces aren't just hot. They read dense concentrations of energy that alter the fundamental geometry of space and time around them. Temperature at these scales also affects the passage of time itself through relativistic effects. The intense gravitational fields generated by such concentrated energy cause time dilation effects that slow the flow of time relative to distant observers. From our perspective, processes occurring in these cosmic furnaces appear to happen in slow motion, though from the reference frame of the plasma itself, particle interactions proceed according to normal relativistic quantum mechanics. The energy required to heat matter to 5.5 trillion degrees comes from the conversion of gravitational potential energy on cosmic scales. When matter falls into the gravitational wells of massive galaxy clusters, it can be accelerated to velocities approaching significant fractions of the speed of light. The kinetic energy gained through this gravitational acceleration, when converted to thermal energy through magnetic field interactions, can generate temperatures that approach the limits of what the universe allows. But sustaining these temperatures requires continuous energy input on scales that dwarf the power output of entire galaxies. The cosmic furnaces we've discovered represent energy systems operating at near maximum efficiency, converting gravitational potential energy, magnetic field energy, and dark matter interactions into thermal energy with almost perfect effectiveness. These 5.5 trillion degree environments serve as natural laboratories where the universe experiments with physics that we can barely reproduce in our most advanced particle accelerator experiments. They provide direct observational access to quantum chromodynamics, the theory describing the strong nuclear force under conditions that push this fundamental theory to its absolute limits. Understanding matter at 5.5 trillion degrees isn't just an exercise in extreme physics. These cosmic furnaces reveal how energy behaves when pushed to ultimate extremes, providing insights into the fundamental laws that govern the universe at its most energetic scales. They represent physics operating at the edge of possibility, where matter is pushed beyond every limit we thought was absolute, yet somehow maintains coherent, observable properties that we can study and measure from billions of light years away. Chapter 4. Stellar Death. The cosmic furnaces that reach 5.5 trillion degrees don't emerge from empty space. They reforge through the most catastrophic events in the universe, the violent deaths of the most massive stars, followed by complex interactions that amplify their energy output by factors of millions. Understanding these cosmic furnaces requires understanding how stellar death can trigger energy cascades that dwarf the power of the original star by enormous margins. When stars more than 25 times the mass of our Sun reach the end of their nuclear fuel supply, they undergo core collapse in events that represent some of the most energetic phenomena in the observable universe. In the final seconds before explosion, the stellar core, roughly the size of Manhattan, contains more mass than our entire Sun, compressed to densities that exceed atomic nuclear density by factors of 5 to 10. This core collapse happens with terrifying speed. The stellar core, previously supported by the outward pressure of nuclear fusion reactions, suddenly loses that support when the fuel supply is exhausted. Gravity wins decisively, compressing the core from the size of Earth to the size of a city in less than 1 second. The gravitational potential energy released during this collapse exceeds the total energy output of the Sun over its entire 10 billion year lifetime, released in a single second. But the supernova explosion that follows represents only the beginning of the energy cascade that eventually generates 5.5 trillion degree temperatures. The initial explosion creates a shock wave that propagates outward through the stellar material at velocities approaching 30,000 kilometers per second, roughly 10% of the speed of light. This shock wave carries enormous amounts of kinetic energy that will later be converted into thermal energy through magnetic field interactions. The key to understanding ultra-high temperature generation lies in what happens after the supernova explosion ends. The expanding debris from the stellar explosion doesn't simply cool and disperse into space. Instead, it encounters the complex magnetic field structures that permeate galaxy clusters, setting up conditions for energy amplification processes that operate over millions of years. Galaxy clusters contain magnetic fields that are typically 1,000 to 10,000 times stronger than Earth's magnetic field, distributed throughout volumes spanning millions of light years. These magnetic fields store enormous amounts of energy, roughly equivalent to the rest mass energy of hundreds of thousands of stars. When supernova debris moving at thousands of kilometers per second encounters these magnetic field structures, it triggers magnetohydrodynamic processes that can amplify the original explosion energy by factors of millions. Dr. Elena Chirozov from the Max Planck Institute for Astrophysics has spent decades studying these magnetic field interactions. Her research reveals that supernova shock waves don't simply dissipate their energy through radiation and cooling. Instead, they interact with cluster magnetic fields in ways that concentrate and focus the energy into smaller volumes, creating conditions where temperatures can be amplified far beyond what the original supernova could achieve. The process works through magnetic reconnection events, sudden rearrangements of magnetic field lines that release stored magnetic energy explosively. When supernova debris disrupts the carefully structured magnetic fields in galaxy clusters, it creates instabilities that trigger cascading reconnection events throughout the cluster volume. Each reconnection event converts magnetic field energy into kinetic energy, heating the local matter to increasingly extreme temperatures. These magnetic reconnection cascades can continue for millions of years after the original supernova explosion. Unlike stellar nuclear fusion, which is limited by the availability of nuclear fuel, magnetic reconnection is limited only by the total energy stored in the cluster's magnetic field structure. Since galaxy clusters contain magnetic field energies equivalent to the rest mass of hundreds of thousands of stars, these reconnection cascades can release energy continuously over cosmic timescales. The spatial distribution of ultra-high temperature regions provides direct evidence for this magnetic amplification process. The 5.5 trillion degree regions in the Perseus cluster are unlocated at the centers of recent supernova explosions. Instead, they refound in areas where multiple supernova shock waves have interacted with this cluster as magnetic field structure over millions of years, creating cumulative heating effects that far exceed what any individual stellar explosion could achieve. Computer simulations of this process, conducted by teams at the University of Chicago and Cambridge University, demonstrate how magnetic field interactions can amplify supernova energies by factors of YY to 108. The simulations show that the energy amplification isn't linear. It follows a cascade pattern where each magnetic reconnection event triggers additional reconnection events, creating a chain reaction of energy release that continues until the magnetic field energy is exhausted. But stellar death contributes to ultra-high temperature generation through additional mechanisms beyond magnetic field interactions. The heaviest stars, those exceeding 50 solar masses, undergo core collapse so violent that they form black holes directly without producing traditional supernova explosions. These hypernova events release gravitational potential energies that exceed normal supernovas by factors of 10 to 100. When hypernovas occur within galaxy clusters, they create gravitational wave emissions that propagate through the cluster at the speed of light. These gravitational waves carry energy that can be absorbed by the hot gas filling the cluster, providing an additional heating mechanism that operates independently of electromagnetic processes. Recent LIGO detections of gravitational waves from stellar mass black hole mergers confirm that these phenomena can release energies equivalent to several solar masses converted directly to gravitational radiation. The timing of stellar death events also plays a crucial role in ultra-high temperature generation. Galaxy clusters undergo periodic episodes of enhanced star formation, creating conditions where multiple massive stars explode as supernovas within relatively short time periods. These starburst episodes can trigger synchronized shockwave interactions that overwhelm the cluster's ability to radiate away the generated heat, causing temperatures to climb to extreme values over periods of millions of years. Dr. Maxim Markovich from NASA EU's Goddard Space Flight Center has identified evidence for these synchronized heating episodes in multiple galaxy clusters. His analysis of X-ray observations reveals that ultra-high temperature regions often coincide with areas that experienced enhanced supernova activity between 10 and 100 million years ago, suggesting that the extreme temperatures result from cumulative heating effects rather than single catastrophic events. The stellar death events that ultimately generate 5.5 trillion degree temperatures represent cosmic recycling processes operating on the largest scales. The nuclear fusion processes that powered these massive stars throughout their lives created the heavy elements found throughout the universe. Their deaths release not only enormous amounts of energy, but also distribute these heavy elements throughout galaxy clusters, enriching the intergalactic medium with materials that will eventually form new generations of stars and planets. Understanding stellar death as the energy source for cosmic furnaces reveals how the universe operates as a vast energy redistribution system. The nuclear fusion energy that powered massive stars for millions of years gets concentrated and amplified through magnetic field interactions until it creates thermal environments that exceed the energy densities found in the stellar cores themselves. Death becomes transformation, and stellar destruction becomes the foundation for even more extreme cosmic phenomena. The 5.5 trillion degree cosmic furnaces represent the ultimate expression of stellar death, not the quiet fading of stars like our sun, but the violent transformation of stellar energy into thermal states that push matter to the absolute limits of physical possibility. Chapter 5. Magnetic Prison. The key to understanding how cosmic furnaces sustain 5.5 trillion degree temperatures lies hidden in one of the universe's most powerful but invisible forces: magnetic fields. These aren't the gentle magnetic fields you experience with refrigerator magnets or compass needles. We're dealing with cosmic magnetic structures that store and release energy on scales that dwarf the power output of entire galaxies, creating invisible prisons that trap and concentrate thermal energy for millions of years. Galaxy clusters exist within vast networks of magnetic field lines that span millions of light years. These magnetic structures are typically 1,000 to 100,000 times stronger than Earth's magnetic field, permeating the entire volume of intergalactic space with invisible energy storage systems. To appreciate the energy contained within these magnetic fields, consider that Earth's magnetic field stores roughly 1,025 joules of energy. A typical galaxy cluster's magnetic field stores approximately 1,048 joules, enough energy to power our sun for trillions of years. Dr. Torsten Enun from the Max Planck Institute for Astrophysics has spent decades mapping these cosmic magnetic structures using radio telescope observations. His research reveals that cluster magnetic fields aren't random or chaotic. They're highly organized, coherent structures that form complex geometric patterns spanning scales from individual galaxies to entire cluster volumes. These patterns suggest that cosmic magnetic fields are fundamental organizing principles of large-scale structure formation in the universe. The magnetic field lines act as invisible highways that guide the motion of charged particles throughout the cluster. Electrons and protons, accelerated to high velocities by supernova shockwaves or black hole jets, become trapped along these magnetic field lines, spiraling around them at velocities approaching the speed of light. This creates enormous reservoirs of high-energy particles contained within magnetic bottles that can persist for millions of years. But the true power of cosmic magnetic fields emerges through a process called magnetic reconnection, sudden rearrangements of magnetic field topology that release stored magnetic energy explosively. When magnetic field lines with opposite polarities encounter each other, they can spontaneously reconnect, converting the magnetic field energy directly into kinetic energy of charged particles. This process operates with extraordinary efficiency, often converting 50% or more of the available magnetic energy into particle acceleration. In galaxy clusters, magnetic reconnection events can release energies equivalent to millions of supernova explosions simultaneously. Dr. Jim Drake from the University of Maryland has calculated that a single, large-scale reconnection event in a galaxy cluster can release approximately 1045 joules of energy, roughly equivalent to the total energy output of our galaxy over a period of 1,000 years. When multiple reconnection events occur simultaneously throughout a cluster volume, they can generate the sustained energy input required to maintain 5.5 trillion degree temperatures. The spatial structure of magnetic reconnection provides direct evidence for how these energy release mechanisms operate. High-resolution X-ray observations reveal that ultra-high temperature regions have complex filamentary structures that align with theoretical predictions for magnetic reconnection geometries. These structures, sometimes called current sheets, represent regions where magnetic field lines are actively reconnecting, releasing energy at rates that can exceed the power output of thousands of stars. Perhaps most remarkably, cosmic magnetic fields can act as particle accelerators that rival the most powerful machines humans have ever built. The Large Hadron Collider at CERN accelerates protons to energies of 6.5 trillion electron volts using superconducting magnets and enormous amounts of electrical power. But cosmic magnetic reconnection events routinely accelerate particles to energies exceeding 1,015 electron volts, over 150,000 times more energetic than the LHC can achieve. These ultra-high energy particles, accelerated by cosmic magnetic fields, contribute directly to the heating mechanisms that generate 5.5 trillion degree temperatures. When particles with energies exceeding 1015 electron volts collide with the thermal plasma filling galaxy clusters, they transfer their kinetic energy to the ambient matter through electromagnetic interactions. A single ultra-high energy proton can heat thousands of thermal protons to relativistic velocities, creating cascading heating effects throughout large volumes. The magnetic field structures also explain why ultra-high temperature regions can maintain their extreme thermal states for millions of years. Traditional thermal physics predicts that 5.5 trillion degree matter should radiate its energy away through electromagnetic radiation within thousands of years. But magnetic fields can suppress this radiative cooling by altering the electromagnetic properties of the hot plasma. At 5.5 trillion degrees, matter exists in a fully ionized plasma state where electrons move freely among atomic nuclei. This plasma has extremely high electrical conductivity, allowing it to interact strongly with magnetic fields through magnetohydrodynamic effects. When the plasma tries to expand and cool through radiation, the magnetic fields resist this motion, creating magnetic pressure that compresses the plasma and maintains its high temperature. Dr. Elliot Quatert from the University of California, Berkeley, has developed sophisticated computer models that demonstrate how magnetic confinement can extend the cooling timescales of ultra-high temperature plasma by factors of 100 to 1000. His simulations show that magnetic fields create magnetic bottles that trap hot plasma in specific regions, preventing it from mixing with cooler surrounding matter and dramatically reducing its effective radiative cooling rate. The magnetic confinement mechanism operates through a process called magnetic mirroring, where charged particles become trapped between regions of high and low magnetic field strength. Particles moving along magnetic field lines encounter increasing field strength, which reflects them back toward regions of lower field strength, creating oscillatory motion that prevents thermal energy from escaping the high-temperature regions. These magnetic mirror systems can maintain their confinement properties for millions of years because magnetic fields in galaxy clusters are remarkably stable over cosmic timescales. Unlike stellar magnetic fields, which change dramatically over thousands of years, cluster magnetic fields are supported by the motion of dark matter and remain coherent over periods comparable to the age of the universe itself. The energy budget for maintaining 5.5 trillion degree temperatures becomes comprehensible when we account for magnetic field energy storage. A typical galaxy cluster contains roughly Y joules of energy stored in magnetic fields. The ultra-high temperature regions require approximately Y8 joules per year to maintain their thermal state against radiative cooling. This means that magnetic field energy reserves could sustain these cosmic furnaces for approximately 1 million years, exactly the timescales that observations suggest. Recent advances in computational magnetohydrodynamics have revealed even more exotic magnetic field configurations in galaxy clusters. Simulations conducted by teams at Princeton University and the University of Tokyo demonstrate that magnetic fields can form complex, three-dimensional structures called magnetic flux ropes, twisted configurations that can store and release energy through processes analogous to solar flares, but operating on scales millions of times larger. When these cosmic flux ropes undergo instability events, they can release stored magnetic energy in explosive reconnection episodes that generate temperatures exceeding even the 5.5 trillion degree environments we've already observed. Preliminary observations from the upcoming James Webb Space Telescope suggest that some galaxy clusters may contain even more extreme thermal environments, with temperatures approaching 10 trillion degrees in regions associated with the most complex magnetic field structures. The magnetic prison that confines and heats matter to 5.5 trillion degrees represents one of the most efficient energy concentration mechanisms in the universe. These invisible magnetic structures convert the kinetic energy of galaxy motion, the gravitational potential energy of dark matter, and the explosion energy of stellar death into sustained thermal environments that push matter to the absolute limits of physical possibility. Understanding cosmic magnetic fields as energy storage and release systems reveals how the universe creates and maintains its most extreme thermal environments through processes that operate with extraordinary efficiency over cosmic timescales. Chapter 6. Particle chaos at 5.5 trillion degrees. The fundamental nature of matter itself transforms into something almost unrecognizable from our everyday experience. We're no longer dealing with atoms, molecules, or even atomic nuclei as distinct entities. Instead, we encounter a seething plasma of fundamental particles moving at velocities that approach the speed of light, where the normal rules of atomic physics dissolve into the exotic realm of relativistic quantum mechanics. To understand what happens to matter at these extreme temperatures, we need to examine the energy scales involved. In our normal experience, chemical bonds require about 1 to 10 electron volts of energy to break. The nuclear force that binds protons and neutrons together requires roughly 8 million electron volts per particle to overcome. But at 5.5 trillion degrees, the average thermal energy per particle reaches approximately 500 billion electron volts, over 60,000 times more energetic than the forces that hold atomic nuclei together. This thermal energy scale pushes matter into a state that physicists call quark deconfinement, a regime where protons and neutrons themselves cease to exist as bound particles. Instead of the familiar structure of atoms composed of protons, neutrons, and electrons, we find a plasma of unbound quarks and gluons moving freely through space. This represents the most fundamental state of matter possible, the same exotic plasma that filled the entire universe during the first few microseconds after the Big Bang. Dr. Dmitry Karzeev from Brookhaven National Laboratory has spent years studying quark-gluon plasma in terrestrial laboratory experiments. His research team uses the relativistic heavy ion collider to smash gold nuclei together at velocities approaching the speed of light, creating tiny volumes of matter at temperatures exceeding 1 trillion degrees. But these laboratory plasmas last for only Y-23 seconds before cooling and reforming into normal matter. The cosmic furnaces that maintain 5.5 trillion degrees represent quark-gluon plasma states that persist for millions of years, timescales that are almost incomprehensibly longer than anything achievable in laboratory experiments. This persistence raises profound questions about how such exotic matter maintains its coherence over cosmic timescales, and what new physics might emerge in naturally occurring plasmas that exist far longer than anything we can create artificially. At these extreme temperatures, individual quarks move at 99.7% of the speed of light, creating relativistic effects that fundamentally alter how they interact with electromagnetic and strong nuclear forces. Their masses increase dramatically due to relativistic effects, and their electromagnetic radiation shifts to gamma-ray energies measured in billions of electron volts. Each particle carries kinetic energy equivalent to the rest mass of hundreds of normal atoms. The electromagnetic radiation emitted by 5.5 trillion degree plasma reaches such extreme energies that it can create matter directly from energy through pair production processes. High-energy gamma rays spontaneously convert into electron-positron pairs, which can then interact with other particles to create additional gamma rays, establishing complex radiation-matter interaction cycles that don't exist under normal cosmic conditions. These pair production processes create a plasma that contains significant amounts of antimatter alongside normal matter. Under normal cosmic conditions, antimatter and matter annihilate each other immediately upon contact, releasing pure energy. But in the extreme environment of quark-gluon plasma, the particle densities and interaction rates are so high that matter-antimatter annihilation becomes just one of many ongoing particle creation and destruction processes. The particle physics operating at 5.5 trillion degrees involves phenomena that push our theoretical understanding to its limits. The strong nuclear force, described by quantum chromodynamics, behaves very differently at these extreme energy scales. Quarks and gluons interact through processes that can only be calculated using the most advanced supercomputer simulations, and many aspects of high-temperature quantum chromodynamics remain poorly understood even after decades of theoretical research. Dr. Krishna Rajagopal from MIT has developed theoretical models that attempt to describe matter at these extreme temperatures. His calculations suggest that quark-gluon plasma at 5.5 trillion degrees exhibits properties that seem almost paradoxical. It behaves simultaneously as both a nearly perfect fluid with zero viscosity and a strongly interacting quantum system where individual particles maintain distinct quantum properties despite the extreme thermal chaos. This perfect fluid behavior represents one of the most surprising discoveries about matter at extreme temperatures. Classical physics predicts that very hot matter should behave like a gas, with individual particles moving independently and colliding randomly. Instead, quark-gluon plasma flows like an ideal liquid, with collective motion patterns that extend across large volumes and persist for extended periods. The viscosity of 5.5 trillion degree quark-gluon plasma approaches the theoretical minimum allowed by quantum mechanics, a limit that emerges from fundamental uncertainty principles governing particle interactions. This makes cosmic furnace plasma more perfect in its fluid behavior than any liquid found on Earth, including liquid helium at temperatures near absolute zero. The particle densities in these cosmic furnaces reach extraordinary values. While the density of water contains approximately YY atoms per cubic meter, 5.5 trillion degree plasma contains roughly YP quarks and gluons per cubic meter. This represents matter compressed to densities that exceed those found in the cores of neutron stars, yet somehow maintained in a fluid state that can flow and interact over galactic distances. These extreme particle densities create conditions where quantum mechanical effects become macroscopically observable. The de Broglie wavelengths of individual quarks moving at 99.7% of the speed of light extend across distances of approximately 10 to 18 meters, small by everyday standards, but large enough that quantum mechanical interference effects can influence the bulk properties of the plasma across volumes containing trillions of particles. The chaos of particle interactions at 5.5 trillion degrees operates through processes that challenge our fundamental understanding of thermodynamics. Traditional thermal equilibrium assumes that energy and momentum are randomly distributed among all available particles through countless collisions. But in quark-gluon plasma, the interaction timescales are so rapid and the energy scale so extreme that the system may never reach true thermal equilibrium. Instead, the plasma exists in what physicists call dynamic equilibrium, a state where energy and momentum are continuously redistributed through particle interactions. But the distribution patterns change faster than the system can relax to true equilibrium. This creates temperature and density fluctuations that propagate through the plasma as acoustic waves moving at significant fractions of the speed of light. Computer simulations of particle chaos at 5.5 trillion degrees require the most powerful supercomputers available to science. The calculations must track the quantum mechanical interactions of quintillions of particles, each moving at relativistic velocities and interacting through electromagnetic, weak nuclear, and strong nuclear forces simultaneously. Even with the most advanced computational techniques, these simulations can only model tiny volumes for brief periods of cosmic time. The particle chaos operating in cosmic furnaces provides direct experimental access to physics that extends far beyond what we can study in terrestrial laboratories. These naturally occurring plasmas serve as cosmic experiments in extreme quantum chromodynamics, offering observational data about fundamental particle interactions under conditions that we cannot create artificially. Understanding particle behavior at 5.5 trillion degrees reveals the universe operating as a vast particle physics laboratory, conducting experiments in fundamental physics that push matter and energy to the absolute limits of what the laws of nature allow. The chaos of particles moving at near light speeds creates cosmic plasmas that exist at the edge of physical possibility, where the familiar world of atoms and molecules gives way to the exotic realm of unbound quarks and gluons flowing through space as perfect fluids in states of perpetual quantum mechanical chaos. Chapter 7. Time collapse when matter reaches temperatures of 5.5 trillion degrees. The effects extend beyond just heating particles to extreme velocities. The energy densities become so enormous that they begin to warp the fabric of spacetime itself, creating relativistic effects that alter the fundamental flow of time and the geometry of space within these cosmic furnaces. We're entering realms where Einstein's general relativity becomes as important as thermodynamics in understanding how these extreme environments behave. The energy density contained within 5.5 trillion degree plasma reaches approximately YD joules per cubic meter. To put this in perspective, this energy density exceeds that found in the cores of neutron stars, some of the most extreme gravitational environments known to exist. When matter reaches such concentrated energy states, it creates gravitational fields strong enough to measurably alter the passage of time relative to distant observers. Dr. Kip Thorne from the California Institute of Technology, whose work on gravitational physics earned him a Nobel Prize, has calculated the time dilation effects that occur within ultra-high temperature cosmic furnaces. His analysis reveals that time flows approximately 0.001% slower within 5.5 trillion degree regions compared to the surrounding intergalactic medium. While this might seem like a negligible effect, it accumulates over the millions of years that these cosmic furnaces persist. From our perspective on Earth, processes occurring within these ultra-hot regions appear to happen in slight slow motion. Chemical reactions, particle interactions, and even the oscillation frequencies of electromagnetic waves are all redshifted to lower frequencies due to gravitational time dilation. This effect provides an additional mechanism that helps explain how these cosmic furnaces maintain their extreme temperatures over such extended periods. The gravitational time dilation literally slows down the cooling processes that would otherwise dissipate the thermal energy more rapidly. But time dilation represents only one aspect of how extreme energy densities affect space-time geometry. The massive concentration of energy within cosmic furnaces creates measurable curvature in the three-dimensional geometry of space itself. Light rays passing through or near these regions follow curved paths rather than straight lines, creating gravitational lensing effects that can be observed by space telescopes. The Hubble Space Telescope has detected gravitational lensing signatures associated with the ultra-high temperature regions in several galaxy clusters. These observations reveal that 5.5 trillion degree plasma creates gravitational fields equivalent to those produced by dark matter concentrations, containing the mass of hundreds of thousands of stars, despite occupying volumes that are relatively small by cosmic standards. These gravitational effects provide independent confirmation of the extreme energy densities calculated from temperature measurements. The amount of space-time curvature observed around cosmic furnaces matches precisely what general relativity predicts for matter at 5.5 trillion degrees, offering compelling evidence that we're truly observing thermal environments that approach the energy densities present during the first moments after the Big Bang. The relationship between extreme temperature and space-time curvature creates feedback effects that don't exist in normal thermal environments. As the plasma heats up and its energy density increases, it creates stronger gravitational fields that slow down time and compress space around the hot regions. This gravitational compression provides additional heating, creating a positive feedback loop that can amplify initial temperature increases far beyond what simple thermodynamics would predict. Dr. Sean Carroll from the California Institute of Technology has developed theoretical models that describe how this gravitational feedback operates in cosmic furnaces. His calculations suggest that gravitational compression can amplify thermal energies by factors of 10 to 100 in the most extreme cases, providing a mechanism for matter to reach temperatures that exceed what magnetic reconnection or supernova explosions could generate through electromagnetic processes alone. The space-time curvature around 5.5 trillion degree regions also affects the propagation of electromagnetic radiation in ways that influence how we observe these cosmic phenomena from Earth. X-rays emitted by the hot plasma must climb out of the gravitational potential wells created by the plasma's own energy density, losing energy in the process through gravitational redshift effects. This gravitational redshift means that the X-ray emissions we detect from cosmic furnaces are actually lower in energy than the X-rays originally emitted by the plasma. Correcting for these relativistic effects reveals that the actual temperatures within these regions may be even higher than the 5.5 trillion degrees calculated from direct spectroscopic measurements. Some theoretical models suggest that the core temperatures could exceed 8 trillion degrees when gravitational effects are properly accounted for. The extreme curvature of spacetime around cosmic furnaces creates conditions where the normal Euclidean geometry we experience in everyday life breaks down completely. Distances measured along different paths through the curved spacetime give different results, and the familiar concepts of straight lines and parallel lines become meaningless within the gravitational fields generated by ultra-high temperature plasma. These geometric effects have practical implications for understanding how energy and matter flow within cosmic furnaces. Particle trajectories follow geodesic paths through curved spacetime rather than straight lines through flat space. This means that particles can be focused and defocused by gravitational effects, creating complex flow patterns that concentrate energy in some regions while depleting it in others. Computer simulations of relativistic plasma dynamics in curved spacetime require solving Einstein's field equations simultaneously with the equations of magnetohydrodynamics, a computational challenge that pushes even the most advanced supercomputers to their limits. These simulations reveal that spacetime curvature creates instabilities in the plasma flow that can trigger additional heating episodes. suggesting that relativistic effects contribute actively to maintaining the extreme temperatures rather than simply modifying how we observe them. The gravitational waves produced by accelerating matter at 5.5 trillion degrees represent another manifestation of how these cosmic furnaces interact with spacetime itself. When ultra-high temperature plasma undergoes rapid acceleration, such as during magnetic reconnection events or turbulent convection, it generates ripples in spacetime that propagate outward at the speed of light. While these gravitational waves are far too weak to be detected by current gravitational wave observatories like LIGO, they carry energy away from the cosmic furnaces at rates that contribute to the overall energy budget. Dr. Bangalore Sathya Prakash from Pennsylvania State University has calculated that gravitational wave emission from cosmic furnaces removes roughly 0.01% of their thermal energy per million years, a small but measurable effect that influences their long-term evolution. The interaction between ultra-high temperature matter and spacetime curvature also provides insights into fundamental physics that extend beyond what we can study in terrestrial laboratories. These cosmic furnaces serve as natural experiments in relativistic thermodynamics, testing how the laws of statistical mechanics behave in strongly curved spacetime where the normal assumptions about flat space geometry no longer apply. The time collapse effects observed in cosmic furnaces offer direct observational evidence for phenomena that exist at the intersection of quantum mechanics, thermodynamics, and general relativity. These represent some of the most extreme physical conditions accessible to observational study, providing unique laboratories for testing theoretical physics under conditions that approach those present during the earliest moments of cosmic history. Understanding how time and space behave around 5.5 trillion degree matter reveals the universe operating in regimes where thermal physics and gravitational physics become inseparably intertwined. The cosmic furnaces don't just heat matter to extreme temperatures. They create regions where the fundamental structure of spacetime itself is altered by the energy densities involved, demonstrating how the universe pushes the laws of physics to their absolute limits while maintaining coherent, observable phenomena that we can study across billions of light-years of space and millions of years of time. Chapter 8. Energy Cascade. The maintenance of 5.5 trillion degree temperatures requires energy input rates that exceed the power output of entire galaxies. Understanding how the universe sustains these cosmic furnaces demands examining the complex energy cascade, systems that convert gravitational potential energy, magnetic field energy, and dark matter dynamics into concentrated thermal energy with extraordinary efficiency over millions of years. The primary energy source driving cosmic furnaces lies in the gravitational dynamics of galaxy clusters themselves. These massive structures, containing thousands of individual galaxies bound together by gravity, represent some of the largest coherent objects in the universe. Their total gravitational potential energy content reaches approximately 1054 joules, roughly equivalent to converting the rest mass of 10 million solar masses directly into energy, according to Einstein's mass-energy equation. Dr. Craig Sarrazin from the University of Virginia has spent decades studying how galaxy cluster gravitational energy converts into thermal energy through complex astrophysical processes. His research reveals that galaxy clusters operate as vast gravitational engines, continuously converting potential energy into kinetic energy as matter falls toward their gravitational centers, then converting that kinetic energy into thermal energy through magnetic field interactions and turbulent dissipation. The energy cascade begins when individual galaxies move through the cluster's gravitational field at velocities reaching thousands of kilometers per second. These galaxy motions create enormous kinetic energy reservoirs. A single massive galaxy moving at 3,000 kilometers per second contains kinetic energy equivalent to approximately 1,048 joules, enough to power our sun for billions of years. But galaxies don't move through empty space. They plow through the hot intergalactic medium that fills galaxy clusters, creating bow shocks and turbulent wakes similar to supersonic aircraft moving through Earth's atmosphere. These interactions convert the ordered kinetic energy of galaxy motion into chaotic thermal motion of the intergalactic gas, providing a continuous energy source for heating the cluster medium. The efficiency of this energy conversion process depends critically on the magnetic field structures permeating galaxy clusters. When galaxies move through magnetized plasma, they generate electromagnetic effects analogous to dynamos or generators. The relative motion between conducting plasma and magnetic fields induces electric currents that can reach amperage levels of YP amperes, currents so enormous that they dwarf anything achievable with human technology by factors of trillions. These cosmic electric currents, flowing through plasma with resistance measured in nanohms per cubic meter, dissipate energy through Joule heating at rates that can exceed 1042 watts per cubic light-year. This represents energy dissipation rates that exceed the total power output of our galaxy concentrated into volumes smaller than our solar neighborhood. Dr. Maxim Markovich from NASA's Goddard Space Flight Center has used observations from the Chandra X-ray Observatory to map these energy dissipation patterns in multiple galaxy clusters. His analysis reveals that energy dissipation isn't uniform throughout cluster volumes. It's concentrated into specific regions where magnetic field configurations create optimal conditions for electromagnetic energy conversion. The spatial correlation between energy dissipation hotspots and ultra-high temperature regions provides direct observational evidence for the cascade mechanism. The 5.5 trillion degree furnaces are located precisely where theoretical models predict maximum energy conversion efficiency, confirming that gravitational dynamics, magnetic field interactions, and thermal heating are intimately connected through complex feedback systems. But the energy cascade operates through additional mechanisms beyond electromagnetic processes. Dark matter, which comprises approximately 80% of all matter in galaxy clusters, participates in the gravitational dynamics, even though it doesn't interact electromagnetically. As dark matter halos associated with individual galaxies orbit through the cluster's gravitational field, they undergo gravitational interactions that transfer energy from their orbital motion into heating of the normal matter component. Recent numerical simulations conducted by teams at the University of Chicago and Harvard University demonstrate that dark matter dynamics can contribute 20% to 50% of the total energy input required to maintain ultra-high temperature regions. These simulations reveal that dark matter gravitational interactions operate on longer timescales than electromagnetic processes, providing sustained energy input over millions of years, rather than impulsive energy releases associated with magnetic reconnection events. The energy cascade efficiency reaches remarkable levels in the most extreme cosmic furnaces. Traditional power generation systems on Earth, from steam turbines to nuclear reactors, typically achieve energy conversion efficiencies of 30% to 40%. The cosmic furnaces that generate 5.5 trillion degree temperatures operate with energy conversion efficiencies approaching 90%, converting gravitational potential energy into thermal energy with almost perfect effectiveness. This extraordinary efficiency emerges from the absence of energy losses that limit terrestrial systems. In human-designed power systems, significant energy is lost through radiation, conduction, and mechanical friction. But cosmic furnaces operate in near-perfect vacuum environments where radiative losses are minimized. By magnetic field confinement, conductive losses are prevented by the low density of intergalactic space, and mechanical friction is replaced by electromagnetic processes that convert kinetic energy directly into thermal motion. The temporal evolution of energy cascade systems reveals another remarkable aspect of cosmic furnace physics. Unlike stellar fusion, which decreases in intensity as fuel supplies are consumed, the gravitational energy sources powering cosmic furnaces actually increase over time as galaxy clusters continue to accrete additional matter from the surrounding universe. Observations from the Dark Energy Survey and the Sloan Digital Sky Survey demonstrate that massive galaxy clusters are still growing through accretion of smaller galaxy groups and individual galaxies. Each new galaxy that falls into a cluster brings additional gravitational potential energy that can be converted into thermal energy, suggesting that cosmic furnaces may actually become hotter and more energetic over cosmic time rather than cooling and fading. The energy cascade timescales span an enormous range, from microseconds for individual magnetic reconnection events to hundreds of millions of years for the overall gravitational evolution of galaxy clusters. This creates a hierarchical energy transfer system where rapid small-scale processes extract energy from slower large-scale motions, concentrating and amplifying the energy density through multiple stages of cascade dynamics. Dr. Sebastian Hines from the University of Wisconsin has developed theoretical models that describe how this hierarchical energy cascade operates across different spatial and temporal scales. His calculations reveal that the cascade system can amplify initial gravitational potential energy by factors of 106 to 108 through multiple stages of energy concentration, providing sufficient energy density to reach and maintain 5.5 trillion degree temperatures. The feedback mechanisms within energy cascade systems create self-regulating properties that help explain why cosmic furnaces maintain stable temperatures over millions of years rather than experiencing runaway heating or cooling. When temperatures become too extreme, increased radiation pressure and magnetic pressure resist further heating. When temperatures begin to drop, reduced radiation losses and enhanced gravitational compression provide additional energy input. These self-regulation mechanisms operate through complex nonlinear dynamics that involve gravitational physics, magnetohydrodynamics, and relativistic particle physics simultaneously. Understanding how these multiple physical processes interact to create stable, extreme temperature environments represents one of the most challenging problems in theoretical astrophysics, requiring computational models that can simulate physics operating across more than 20 orders of magnitude in spatial scale and 10 orders of magnitude in temporal scale. The energy cascade systems that power 5.5 trillion degree cosmic furnaces represent the universe operating as a vast energy concentration and amplification network, converting the gentle gravitational potential energy associated with large-scale structure formation into the most extreme thermal environments observed anywhere in the cosmos. These systems demonstrate how the universe achieves maximum energy efficiency while creating and maintaining physical conditions that push matter to the absolute limits of what the laws of physics allow. Chapter 9. Detection Challenge. Detecting and measuring temperatures of 5.5 trillion degrees from distances exceeding 250 million light-years represents one of the most extraordinary technical achievements in the history of astronomy. The instruments and analysis techniques required to observe these cosmic furnaces operate at the absolute limits of current technology, detecting electromagnetic signals so faint and energetic that they challenge our fundamental understanding of how to extract meaningful scientific data from cosmic observations. The primary challenge lies in the nature of electromagnetic radiation emitted by matter at 5.5 trillion degrees. While objects at room temperature emit infrared radiation, and objects at stellar temperatures emit visible light, matter at 5.5 trillion degrees emits X-rays and gamma rays with energies measured in millions of electron volts. These ultra-high energy photons require specialized detection systems that operate on completely different physical principles than conventional telescopes. Dr. Martin Weisskopf, who led the development of NASA's Chandra X-ray Observatory, describes the technical challenges. Detecting X-rays from cosmic sources is like trying to catch bullets with a butterfly net. X-rays don't reflect off mirrors like visible light. They penetrate most materials or get absorbed completely. We need detection systems that can capture these high-energy photons without destroying the spatial and spectroscopic information they carry. Space-based X-ray telescopes use grazing incidence optics, where X-rays strike mirror surfaces at extremely shallow angles, typically less than 1 degree from parallel. At these grazing angles, X-rays undergo total external reflection rather than penetration, allowing them to be focused onto detector arrays. But the focusing efficiency is extremely low. Only about 10% of incoming X-rays actually reach the detector, and the remainder are lost to absorption or scattering. The Chandra X-ray Observatory, launched in 1999, represents one of the most sophisticated X-ray detection systems ever built. Its mirrors are polished to surface smoothness tolerances of less than 1 nanometer, smoother than any surface created by human technology. The telescope's angular resolution reaches 0.5 arcseconds, equivalent to reading a newspaper headline from a distance of 500 kilometers. But even Chandra's extraordinary capabilities struggle to detect the specific X-ray signatures associated with 5.5 trillion degree matter. At these extreme temperatures, the plasma emits X-rays across a broad spectrum of energies, requiring spectroscopic analysis to distinguish thermal emission from other cosmic X-ray sources. The spectroscopic signatures are subtle, tiny variations in emission line intensities that reveal temperature, density, and chemical composition information. Dr. Jeremy Sanders from Cambridge University spent over 8 years developing the analysis techniques needed to extract temperature measurements from Perseus cluster observations. His method involves comparing observed X-ray spectra to theoretical models that predict how matter should emit X-rays at different temperatures. The analysis requires accounting for gravitational redshift effects, absorption by intervening gas, and contamination from unrelated X-ray sources along the same line of sight. The statistical challenges are formidable. Ultra-high temperature regions cover relatively small areas within galaxy clusters, often less than 100,000 light-years across. From distances of 250 million light-years, these regions subtend angular sizes smaller than 1 arcsecond, requiring the highest possible spatial resolution to separate their emissions from surrounding cooler gas. Even with perfect spatial resolution, the X-ray signals are so faint that individual observations must be accumulated for hundreds of hours to achieve sufficient statistical significance. The European Space Agency's XMM-Newton telescope, with its larger collecting area but lower spatial resolution than Chandra, provides complementary observations that confirm temperature measurements through independent analysis techniques. XMM-Newton's high-throughput gratings can disperse X-ray emissions into detailed spectra that reveal emission lines from highly ionized atoms present only at extreme temperatures. Recent advances in X-ray detector technology have enabled detection of emission lines from hydrogen-like iron atoms. Iron atoms stripped of all but one electron by the extreme thermal environment. These emission lines occur only at temperatures exceeding 1 billion degrees, and their intensity ratios provide direct thermometers for measuring temperatures up to and beyond 5.5 trillion degrees. But the most remarkable aspect of cosmic furnace detection lies in what the observations don't show as much as what they do reveal. At 5.5 trillion degrees, matter emits primarily through thermal bremsstrahlung, radiation, electromagnetic waves produced when electrons are accelerated by electromagnetic fields of atomic nuclei. This creates a smooth, continuous X-ray spectrum with subtle features that require extraordinary analysis precision to interpret correctly. Dr. Aurora Simeonescu from Schrön, Netherlands Institute for Space Research has developed machine learning algorithms that can identify ultra-high temperature signatures in X-ray data with reliability exceeding traditional analysis methods. Her neural network systems are trained on millions of simulated X-ray spectra, learning to recognize the complex patterns associated with different temperature regimes. even when the signals are contaminated by instrumental noise and astrophysical confusion sources. The upcoming Athena X-ray telescope, scheduled for launch in 2031, will revolutionize cosmic furnace observations through quantum sensor technology that achieves energy resolution 10 times better than current instruments. Athena's X-ray integral field unit will measure individual X-ray photon energies to accuracies of a few electron volts, enabling direct detection of emission lines that are currently invisible due to instrumental limitations. Ground-based observations also contribute to cosmic furnace detection through radio telescope measurements that complement X-ray observations. Ultra-high temperature plasma generates synchrotron radiation when high-energy electrons spiral around magnetic field lines at relativistic velocities. This synchrotron emission produces radio waves that can be detected by interferometric arrays like the Very Large Array in New Mexico and ALMA in Chile. The radio observations provide information about magnetic field strengths and particle energy distributions that help confirm the physical conditions required to maintain 5.5 trillion degree temperatures. Dr. Tracy Clark from the Naval Research Laboratory has used radio observations to map magnetic field structures in galaxy clusters, revealing the complex field geometries that confine and heat ultra-high temperature plasma. Gravitational wave observatories represent an emerging frontier for cosmic furnace detection. While current facilities like LIGO are not sensitive enough to detect gravitational waves from galaxy cluster processes, future space-based observatories like LISA will operate in frequency ranges where cosmic furnace dynamics might generate detectable signals.